Okay, so today we are happy to have Jean Gutt, who will tell us about Ekeland-Hofer capacities. It's coming from positive S1 equivariant symplectic homology.
Well, thank you, Paddy. It's a pleasure to talking here in the Zoominar. So everything I'm going to talk about is joint work with Vinicius Ramos. And I should put first a disclaimer is that this talk is going to be about a highly technical result, but I'll try to start by introducing why we were interested in the result, a bit telling a story, and then really delving into technicalities. So, I mean, to go very back in the story is basically we know since Darboux theorem that all symplectic manifolds locally are the same, and therefore, if we want to have invariants to study symplectic manifold, they have to be of a global nature. And one of the first symplectic invariant, like non-trivial invariant that came about are what's called symplectic capacities, and they came after Gromov non-squeezing theorem. So to recall what a symplectic capacity is, it's a function which will assign a number to every symplectic manifold. So a symplectic capacity is a function which assigns a number to every symplectic manifold, or in a restricted class, so which assigns a number to each symplectic manifold. And let me define, I have x omega, my symplectic manifold, and the number is so C of x omega. It's a positive real number or plus infinity, such that it satisfies two axioms. First is if I have a symplectic embedding from manifold x to manifold y, then the number associated to s is x is less than the number associated to y. So if x omega symplectically embeds into x prime omega prime, then C of x omega is less or equal than C of x prime omega prime. And I know I haven't defined what a symplectic embeddings is, so it's a smooth embedding which preserves the symplectic structure so that the pullback of omega prime would be omega. And the second axiom, it's a symplectic invariant in the sense that if you take a positive real number, then the number associated to x and r times omega is r times the number associated to x omega. So examples of symplectic capacity, well, we of course have the function that associated 0 respectively plus infinity to every symplectic manifolds. Those trivially satisfies those axioms. We also have the function which associates the volume to the correct power. So if the manifold is of dimension 2n, you take the n square root of the volume. Those are symplectic capacity, but they are not like the most useful, or are not like intrinsically symplectic. So we have other examples in them. There's from the Gromov non-squeezing theorem, there's what we call the Gromov width, which is the size of the largest ball one can symplectically embed in the symplectic manifold. So this is the supremum over R such that there exists a symplectic embedding from the standard ball of size R in R2n with standard symplectic form in the manifold x omega. And I'm not going to define anything. I'm just going to say since 1985 and this Gromov width, we have built an entire zoo, I want to say, of symplectic capacity. And just to cite a few names, there's a capacity that has been defined by Hofer and Zehnder, a capacity which has been defined by Viterbo. There is a Lagrangian capacity defined by Chelebach and Moncke. There is a cube capacity defined by Michael Hutchings and myself. And then there are also sequences of capacities. So there's in dimension 4, there are capacities, a sequence indexed by natural number coming from embedded contact homology, which have been defined by Michael. Then there are a sequence introduced by Ekeland-Hofer, and there's a sequence which I introduced with Michael using positive S1 equivariant symplectic homology. Those are not an exhaustive list. There's many others, but here I took like some of those which are the most used. And what I'd like also to point out is that most of those capacities come from very different world, or like definition is very different. Like the Hofer-Zehnder comes from dynamics, Viterbo capacity come from homology, Lagrangian capacities come from looking at area of a pseudo-holomorphic disk. The cube capacity is very similar to the Gromov-Witz, it's like the size of the largest cube. And then the ECH come from what's called embedded contact homology. The Ekeland-Hofer, we're going to define them a bit later, but they come from variational functional. And the capacities I define with Hutchings are coming also from some type of homology. Now, since we have many symplectic capacities, a question I think which is very natural and I like is, do we have an axiomatic characterization of some capacities? In the sense, we know capacity satisfies the two axioms here above. So this axiom 1 and this axiom 2. And question is, can you add some axioms so that a capacity is uniquely characterized? And maybe let me motivate a bit more this question about why characterization is interesting, or why did I got interested in finding a characterization for symplectic capacity, is if one look at a convex set in R2N, and by convex I mean affine convex, like the line segment between any pair of points is inside the domain, then result by, I want to say many people, is those capacities that some of the capacity that I've shown above. So this Hofer-Zehnder capacity, the Viterbo capacity, the first Ekeland-Hofer capacity, and the first capacity coming from positive S1 equivariant symplectic homology, all are the same and are measuring the period of the shortest periodic orbit on the boundary of the domain. Yeah, so the kind of diffuse some dynamical property, but the fact that they come from different worlds but are still all equal on all convex sets kind of is very intriguing. And to put a remark is that all those capacities are called Ball normalized, are what's called Ball normalized. That means that on the ball of size 1, or let's say the ball of radius 1, they are equal to pi, and they have the same value on the cylinder of radius 1, where the cylinder of radius 1 is the cylinder inside R2N, so it's the disk in the coordinate plane x1, y1 times R2N minus 2. So it's disk times R2N minus 2. Yeah. And then there's a well-known conjecture, which was called the strong-Viterbo conjecture, that say, oh, then maybe all ball normalized capacities coincide on all convex sets in R2N. And Pazit and Yaron destroyed that conjecture a few months ago by providing a counterexample. But it's still very intriguing that all those capacities coincide, and the counterexample kind of fails, but by a very tiny quantity, I want to say. And therefore, there's still a conjecture which remains, is that the ball normalized coincide on a convex domain with a symmetry. We know it's true if the convex domain have an S1 symmetry, but maybe if they have only a Z2 symmetry, it still holds. So is that all ball normalized? All ball normalized capacities agrees on centrally symmetric convex domains in R2N. And a very strong motivation for such a conjecture is a result by Yaron and Arstein-Aviden, is that this would imply an old conjecture by Mahler. So if this conjecture were to be true, this would imply Mahler conjecture. Mahler conjecture is in convex geometry. It's about if you take a centrally symmetric convex domain in R2N and you take the product with its dual and you take the volume of the product, then you have always a bound on that volume. This would imply Mahler conjecture. And for the anecdote, Mahler conjecture was formulated like in a paper published in 1936. I think Mahler proved it in dimension 2 around in that period, and it was proven in dimension 3. It was 2018, like very recently, and it's still completely open in higher dimension. So now let's a bit go back to symplectic capacities, and we now have many symplectic capacities, and we kind of want to say how are they related? Can we have an axiomatic characterization? To relate the other capacities, the other examples of capacities I've put, even though I haven't defined them, and let me be here, I should put a really careful sign in the I'm just going to put statement removing any and all assumptions, and there are some in one of those statements that are very strong, but it's just to give an idea. So, but I should say. So the first statement, there's not so many assumptions. It's to relate the ECH capacities and the volume, is that the limit of the ECH capacities squared divided by K, this is one recover the volume. Yeah. So in my examples here above, there's a link between this sequence of ECH capacity and this volume, which was another capacity. And the other result would relate this Lagrangian cube capacity and the capacities coming from positive S1 equivariant symplectic homology. And that's where I say has to be very careful about this statement. I'm removing all assumption, but it's only proven in a restricted family of cases. Is that the limit as case goes to infinity of this family of capacity coming from S1 equivariant symplectic homology divided by K is equal to the Lagrangian capacity of X, and this is also equal to the cube capacity of X. So kind of all the examples we know are somewhat related in one way or another. And the main theorem I want to talk about today is a relation between the, I want to say, the last family that was kind of alone, is that for any star-shaped domain X in R2n, X in R2n, and for any positive natural number, we have that the Ekeland-Hofer capacity of X is equal to the case capacity coming from positive S1 equivariant symplectic homology. So in a sense, that's like a good and bad news. Good in the sense, oh, that's great, that's what we do with variational method is the same as what we do with equivariant homology, it kind of relate all the capacity. Kind of bad news in the sense, it also, in my mind, means we should be happier the more diverse capacities we have, because it would say we have very different symplectic invariants on our manifold. And it's kind of say we are not very imaginative when we try to build capacities. I mean, I'm put this as main theorem, main statement, but so far, since I haven't defined any of the two quantities on the equal sign, it doesn't make a lot of sense. So the rest of the talk is going to be me trying to define those two quantities and then waving my hand as why you should believe that they are equal. And I also have to say that since I'm in Princeton, I was talking with Helmut, and I've learned that so the Ekeland-Hofer get the capacity at the end of the 80s, and in 1988, Fleur and Hofer made a talk at the MSRI, where Fleur had kind of this visionary intuition that the Ekeland-Hofer, so I found notes by Alan Weinstein, where Fleur in a talk said that the Ekeland-Hofer capacities should come from some type of S1 equivariant symplectic homology. So one can also view this statement as like a formal version of Fleur's kind of visionary intuition. So let me go and define, let me start by the capacities from positive S1 equivariant symplectic homology. And let's really stick to everything now is I'm only taking star-shaped domain in R2n. By star-shaped domain, I mean star-shaped with respect to the origin. And that means that the radial vector field is everywhere transverse to the boundary. So that's now X is always going to be a star-shaped domain in that sense. And now let lambda 0 be the one form on R2n, which is 1/2 sum of xi dyi minus yi dxi. Assume that the boundary of X is a smooth hypersurface that I will denote sigma, and then lambda 0 restricted to sigma, which I will call alpha, is a contact form and I mean by that alpha wedge d alpha to the n-1 is never vanishing. And in this situation, we have the Reb vector field. So R alpha, which is defined by the contraction by this vector field of d alpha is 0 and alpha of R alpha is equal to 1. So I'm saying every star-shaped domain is naturally endowed with a vector field on its boundary, assuming the boundary is smooth. Another way to view this Reb vector field is if the hypersurface is the regular level set of a smooth function from R to N to R, then the Reb vector field is proportional to the Hamiltonian vector field of that function. Another way to view that vector field is if at every point on the boundary you take the unit normal vector, and then you say R to N is Cn with natural complex structure J, then J times this unit vector field at every point is now vector field tangent to the hypersurface, and that again is proportional to the Reb vector field. So it's kind of a very natural vector field. Yeah. And then a periodic orbit of the Reb vector field is a map. So a periodic orbit, I want to say a periodic Reb orbit, is a map gamma from S1 to R to N, such that gamma dot is R alpha at point gamma t. So you might wondering why am I suddenly doing all this? So those capacities coming from positive S1 equivariant symplectic homology is there will be a homology which will be R filtered, and those capacities are going to be the level of filtration at which the homology changes. So all I'm doing now is introducing what is this homology, what are the generators of the complex, and what will be the homology, and then the capacities are going to be like just the spectral values of this homology. So the period of the periodic Reb orbit, I call it T, that is also called the symplectic action, is the integral of the one form over gamma. Then, okay, a bit as in Morse theory, I need so the generators of the complex are going to be those Reb orbits, but I need them to be non-degenerate. So periodic Reb orbit is non-degenerate if one is not an eigenvalue of the Poincaré return map. So if one is not an eigenvalue of the Poincaré return map, and the Poincaré return map is the differential of the flow after the period of the orbit. So it's a map from the tangent space at the start of the orbit to itself, and it's just differential of the flow. And to ask that you can view it as a matrix, and to ask that it does not have one as an eigenvalue is the equivalent in most, for function, if you have a point, you say it's non-degenerate if its Hessian doesn't have 0 as an eigenvalue. It's really the equivalent in the dynamical setup. So if your orbit gamma is non-degenerate, one can associate an integer number to it, which is called the Conley-Zehnder index. And this measures how much does the flow winds around the orbit. Now, assume that all gammas, all periodic orbits are non-degenerate. And this is true for a generic star-shaped domain. Then one can define a homology. So we can define positive S1 equivariant symplectic homology, which I will denote by CH of X. this notation is because the Alexandre Wancha and Frédéric Bourgeois proved that in the case where contact homology is well defined, this positive S1 equivariant symplectic homology is isomorphic to contact homology. And so I prefer to just denote it CH, even though I'm still talking about symplectic homology, just because it's shorter and I don't have many indices to carry. So we can define the positive S1 equivariant symplectic homology. So it is the homology of a chain complex generated by the periodic Reb orbit. So it is the homology of a chain complex freely generated over the rational by the good periodic Reb orbit So by good, the definition is it's not bad. And that has to do with the parity of the index of the iterate of an orbit with respect to the simple underlying orbit. So we say an orbit is bad if its index doesn't have the same parity as the index of the underlying simple orbit. And so there's the complex. I'm just saying there exists a differential and it is filtered over R by the symplectic action. By the symplectic action. And so I can talk about the filtered homology. And now for star-shaped domain, so for our X, which is a star-shaped domain, the homology of X is a copy of Q in degree n+1, n+3, n+4, and so forth. So if star is in n+1 plus 2n and 0 otherwise. And I'm using here the French convention. That's because I'm insufferable. I'm saying it's the correct convention that 0 is a natural number. But so it the homology really starts in degree n+1, and then it's n+1, n+3, n+5, and so forth. And then definition of the capacity, it's the level of filtration at which the homology changes. So to be a bit more precise, so this CK of X is the smallest L such that a degree, and now I want my capacity to start at 1, so it's a degree n-1 plus 2k generator of this positive S1 equivariant symplectic homology can be represented by a linear combination of periodic Reb orbit, all of which have action less than L. So can be represented by a linear combination of Reb orbits all of which have action less or equal than L. So in other words, C1 is I look at the homology in degree n+1 and I just increase the filtration until I see the homology in degree n+1. For C2, I look at the homology in degree n+3 and I look at what level, what is the smallest level of filtration at which I see the homology and so forth. Yeah, that's the idea of those capacities. So, and the good thing is with those capacities, with Michael, we have explicit formula for large classes of domain, like for all convex and concave toric domain, we have like very explicit formula for those capacities. Now,
And sorry, may I?
yes, sure. I'm not hearing you.
Sorry, better now?
Yes.
Okay. We don't a priori know that the homology is one-dimensional, right? So you're saying any generator becomes or do you pick a favorite one?
No, I'm saying as you take the lowest filtration such that you have a generator of the homology. So okay, I'm being slightly lousy in my definition because I just want kind of to give the idea, but it would be you have like the inclusion from the homology filtered by L to the full homology, and then you have the map, and in the full homology you have like the you take the smallest filtration such that the generator survives in the entire homology.
Right. So basically, like you said, like a spectral number.
Yes.
But when you say the generator survives, do you
a generator?
Any generator of that degree?
Yes.
Okay, thank you.
Yeah, I said the, but it's that I shouldn't say.
No, you did say but I wasn't sure if there is a favorite one.
No. Thanks. And then let me. Yeah, I was saying this talk was technical, so now technicalities is going to increase when I try to define what are the Ekeland-Hofer capacities. So, okay, so let E be the Sobolev space, which is H1/2 of S1 to R to N. So this is the set of L2 map from S1 to R to N. So they have a Fourier series gamma of the form sum over all integers of gamma k e 2 pi j0 kt. So those are the L2 map such that the H1/2 norm is finite. So such that gamma, let me take the square of that norm, the H1/2 norm. So this is gamma 0 squared plus the sum of over all integers of absolute value of k, gamma k squared, that you want it to be finite. That's H1/2. And H1/2 admits an orthogonal splitting with respect to this Fourier decomposition in positive, 0, and negative frequencies. So you have E plus, E0, and E minus. So E plus, this is the set of elements in H1/2 such that it only has positive frequency. So if k is negative or 0, then gamma k is 0, and E0 is the set of function which only has a 0 frequency, and E minus only has negative frequency. And then one has an action associated to any elements in H1/2, which you can define, it is 1/2 the norm of gamma plus. squared minus gamma minus squared, where gamma plus is the projection of gamma on E plus, and gamma minus is the projection of gamma on E minus. Now, let H from R2n to R be a Hamiltonian, which is quadratic outside the compact set, Hamiltonian quadratic outside a compact set. And the image to have in mind about the kind of the Hamiltonian I will want is I have my star-shaped domains that I put flat, and the Hamiltonian I want to take is essentially 0 inside my domain, and then is of the form constant times norm of x squared outside the domain. That's the type of Hamiltonian we want to consider. And then one has a Hamiltonian action functional AH of gamma. So this is A of gamma minus the integral from 0 to 1 of H of gamma of t dt. That is the Hamiltonian, and it's the usual Hamiltonian action functional. Okay. Now I have to introduce two indices to get finally to the capacities. It's a long definition to get to Ekeland-Hofer capacity. So right now it's just to say we are in this space H1 half, and we have a Hamiltonian where our star-shaped domain is kind of the a level set of our Hamiltonian. And why do we go to H1 half is because we are interested in the Hamiltonian action functional, and it has a gradient flow, and H1 half is the space where the flow is complete. That's why we go to H1 half and don't stick to nicer space. That's kind of the key. Now, to introduce some indices, so for an S1 invariant subspace of E, so of H1 half, so S1 invariant subspace, I'm going to define two index. And when I say S1 invariant, I mean related to reparametrization of loop, right? A theta acting on a loop gamma of t is gamma at t plus theta. That's the S1 action. So if I have an S1 invariant subspace, I have a classifying map for F from Y times the total space of the universal principal S1 bundle, quotient by the diagonal S1 action, to the base of this universal principal S1 bundle, which is Cp infinity. And that induces a map in cohomology. So I have a map F star from the cohomology of Cp infinity to the cohomology of this product of Y times ES1 quotiented by the S1 diagonal action. And that is precisely the Borel definition of S1 equivariant cohomology of Y. So in the case where the S1 action on Y would be free, that cohomology is the cohomology of the quotient of Y by this free S1 action. Now, first index, so definition, the Fadel-Rabinowitz index associated to Y is the max over all integer number such that F star U to the K minus 1 is non-zero, where U is the generator is the degree 2 generator of the ring cohomology of CP infinity, where U is a generator, degree 2 generator of the ring cohomology of CP infinity. And now that was first index that I needed, because Ekeland-Hofer introduced another index based on the Fadel-Rabinovitz index, which is going to be used to define the capacities. So Ekeland-Hofer introduced a group gamma, which is a subgroup of the group of homeomorphism of H1/2. And so an element H is in gamma if it is of the form, so if it is of the form H of X is equal to e to the gamma plus of X times X plus. And when I say X plus, I mean the projection on this E plus part of E. So E, if you recall, there's an orthogonal decomposition in 3 spaces where the Fourier series have only positive, negative, or 0 frequencies. And when I rewrote in the following plus, 0, or minus, I mean projection on each of those 3 subspace. So it's of the form H of X, so X is an element in E, of E gamma plus times X plus, plus I'm not touching X0, the 0 frequency, plus E to the gamma minus of X times X minus plus K of X. So gamma plus and gamma minus are maps from H1/2 to R. I want them to be continuous, S1 invariant, and I want them to map bounded set to bounded set. So I'm mapping bounded set to bounded sets. And K is the map from E to E, which is continuous, S1 equivariant, and map bounded set to precompact set. Bounded sets to precompact sets. Okay, that's a subgroup of the group of homeomorphism of H1/2. And then oops, sorry, my hand slipped. So let S plus, that is the unit sphere in E plus. Right, and then now find definition, the Ekeland-Hofer index of Y, where Y is an S1 invariant subspace in H1/2. So this is defined as the infimum over all homeomorphism in my subgroup gamma of Fadel-Rabinovitz index of H of Y intersect with S plus. Yeah. And then let H be as above. So you think of it as zero inside X and quadratic outside. And then for definition for a positive integer and a Hamiltonian as above, we define the case Ekeland-Hofer capacity of that Hamiltonian H to be, to be the infimum of the supremum of AH of Y, such that Y is S1 invariant and the Ekeland-Hofer index of Y is at least K. And then the case Ekeland-Hofer capacity of X is the infimum over all, I want to call them admissible Hamiltonians. So really think, I mean, the idea to have in mind is zero inside X and of the form constant times norm of X squared outside X. So take all those Hamiltonian and then you take the infimum of the Ekeland-Hofer capacity of H for those Hamiltonian. And that's the Ekeland-Hofer capacity. So I have to point out that the Ekeland-Hofer capacities have been defined at the end of the 80s and have been computed for ellipsoids, for polydiscs, and that's it. Like since 35 years, they are, I mean, maybe you have like a very good intuition about what they are from the definition, but for me, that was not the case at all. It's really hard to compute and to get a grasp of that. So now, okay, I still have 15 minutes to try to wave my hand as why can those two things be the same. The key idea will be to say, to not go to the step where they are equal to X, but to stay at the Hamiltonian. So it's to say, oh, for the S1 equivariant symplectic homology, there's also a direct limit of Hamiltonian, which also look like this. So we can define an S1 equivariant capacity associated to H, and then to X, it will be the same formula. So if we could prove it for a given Hamiltonian, we kind of win. That was the first remark. Then the first proposition, I'm just going to put a list of statements and kind of wave my hand as what are the successive steps in how to reach that those two are the same. So proposition one is if H, I want to call, let's say H is admissible in the sense it's really of the roughly zero and of the type constant times norm of X squared. I mean, there are slight details here, but that's kind of the image to have in mind. Then we can redefine CK Ekeland-Hofer of H to be the infimum over number C, such that the Ekeland-Hofer index of the set where the sublevel set of the action functional, so all the points in H1/2 such that AH is less or equal than C, such that the index of that set is at least K. No? So it was just, the difference was we don't have to look at all S1 invariant subset. We can restrict to only a subset of action function, like Hamiltonian action functional less than a constant. And then definition, let me introduce a quantity that I will call kappa c. So this is the max over j's such that there exists an element in the image of the continuation map from the positive S1 equivariant Floer homology filtered by C in degree 2j plus n minus 1 associated to H to the unfiltered, so FH, the Floer homology S1 equivariant positive associated to H. So the idea here is really, you look at, you have this Floer homology associated to H, and you fix a level C, and you just say, what is like the highest degree in which this homology is non-trivial? That's kind of what I'm trying to write down here. But there's one more condition, is like such that the U map, which decreases the degree by 2, uj of sigma, is non-zero. So we know that at the end, the symplectic homology, as I say, is in degree n plus 1, n plus 3, n plus 5, n plus 7, and so on. And so this quantity is you fix a Hamiltonian, fix a filtration by the action, and you just say, okay, I see the degree n plus 1, n plus 3, n plus 5, and then maybe I see the degree n plus 17, but I don't see the degree n plus 7, so that would be 3. Yeah, it's like the highest degree you see such that they are continuous, like you don't have any gap jumping from 2 to 2. And then the next proposition, which since I haven't put a definition, could also be a definition, is you can define the K capacities from positive S1 equivariant homology associated to a fixed Hamiltonian to be the infimum over C, such that this quantity kappa C is at least K. And then I'm claiming that the infimum over H of those quantities, the usual capacities we know. And now from those two propositions, so from this proposition and this proposition, the only thing we have to show is that the Ekeland-Hofer index of that set, of the set where the action functional is bounded above by C, is equal to this kappa C. So if you can prove the Ekeland-Hofer index is kappa C, then you win. And that's exactly what we're going to do. And for that, we have like a big technical statement. So the main technical statement is that for such a given Hamiltonian, we can define a Morse homology directly for the Hamiltonian action functional in this H1/2 setting that was done in the non-equivariant case by Abbandandolo and Meyer, because they noticed that yes, stable and unstable manifold are infinite dimensional, but the intersections are transverse and finite dimensional. So we kind of win. So we can really define directly a Morse complex and like S1 equivariant Morse, and there's also a filtration directly for the action functional. And what we showed is this is chain complex isomorphic to the Floer complex defined to use S1 equivariant Floer theory filtered by C with the same Hamiltonian. So that's kind of the main technical statement, is that those two, you can define Morse homology for the action functional, you can define Floer homology, and those two are chain complex isomorphic. And then I'm not putting assumption, but we are really stuck to the case of star-shaped hypersurface in R2N. Like it won't work for general manifolds. And the the consequence.
It won't work in the sense that you are aware of counterexamples, or that your argument specifically seems to fail.
Well, first of all, this kind of Morse homology is not very defined for general manifold. There's one or two assumptions, but then I'm not aware of counterexamples. I have to say, it's like our argument will fail dramatically because we need the manifold to be parallelizable. So you can do it for tori, but essentially that's it. Other than that, we have no clue how to reach, and we need very fine control on many estimates. So
I see. So there's no counterexample, but you would not necessarily expect it to be true because it seems to be very specific.
I would not. No.
I see. Thank you.
You're welcome. And kind of the main consequence of that theorem is that this quantity, which I defined above, this kappa C associated to H, let me then put an H here. This kappa C is the Fadel-Rabinowitz index of the set where the Hamiltonian action functional is non-zero and bounded above by C. And of the intuition we had, like, oh, maybe like this kappa C was built to look like a Fadel-Rabinowitz index. It's actually like formally, yes, it's the same, except you have like you need to take a quotient or like a truncated by everything of negative Hamiltonian action. And then, oops, what's happening? Why is it? And then now 2 lemma left. The first lemma is that the Ekeland-Hofer index associated to this set where the action functional is less than C, this is less or equal than the Fadel-Rabinowitz index of the set where this set where the Hamiltonian action functional is between 0 and C. And that surprisingly was an easy lemma. And then the second lemma, which was the most painful, is that the Ekeland-Hofer index of this set AH less or equal than C, this is greater or equal than this kappa C of H. This lemma too was the most painful. Just to say why was it the most complicated for us to build is the Ekeland-Hofer index. If we go back to the definition, it's kind of really hard to compute. You know, it's like an infimum over all element in a group of homeomorphism of the, sorry, let me point it out where it is. It's like here. It's the infimum of all element in a group of homeomorphism of Fadel-Rabinowitz things of an intersection. And here, what we use is to prove this is a proposition by just like Hofer, maybe Zender, maybe more people, that if X is X is already my manifold. So if I don't know, K is a linear subspace of E plus, then the Ekeland-Hofer index of K direct sum with E0 direct sum with E minus is equal to 1/2 dimension of K. So the key point is now we have to find in the set where the Hamiltonian action functional is bounded above by C, we have to find a correct linear subspace of dimension twice this, and that's exactly what we do. But there and that's why I say it was painful. We had to be really clever and control everything so that you have an entire linear subspace lying there. And yeah, I think I'll stop there because it's time, and that was very technical.
Okay, thank you, John. Any questions?
I had a question about the star-shaped assumption. So I might have missed something, but is Ekeland-Hofer even defined at all for anything more general than star-shaped domains?
So Ekeland-Hofer defined indeed for more general than star-shaped domain, but our proof, we kind of are stuck to the star-shaped domain to really have that the standard one form is a contact form and everything works really well, and we can control everything.
I mean, didn't you sort of needed this whole Fourier decomposition of functions on R2N? How do you generalize that to other manifolds?
I forgot how they did, to be fair, because I always stick to R2N, but I know that that it has been pushed to other manifold, but not to all manifold. But sorry, I'm not very precise here. The short answer is I forgot how.
Okay, thanks.
But here's Helmut. So yeah, so the problem is that we work in H1/2, which is if you are on an arbitrary manifold, it's a well-defined topological space, but not a manifold. So it's not a Hilbert manifold, except for example, quotients of R2N by some linear group or so, which means, for example, tori. So on tori, the space of H1/2 maps is actually a Hilbert manifold, but not in general. That's some of the problems. And then if you work in H1/2, of course, you have a flow. If the H1/2 space is a manifold, so you get an ODE there. But in this case here, the questions with intersection problems using these flows are actually rather nice. And that is what we use, for example, for this lemma, I mean, for this result in this intersection result and so on. But I think Abodandolo and Meyer studied the question if one can use such a kind of setup in more generality. And they showed that you can, that the intersection problems can have generic intersections of any dimension you want if you connect the same critical points. So it's really a big mess to using these ideas which we used in R2N, in the loop space of R2N. So in general, a lot of things can go wrong.
Jean, am I right that you somehow avoided using directly this group gamma?
Yes and no. So kind of this group gamma correspond to roughly it contains flow by the gradient of the Hamiltonian action functional. So that's that we have to use that.
Mm-hmm.
No, that we cannot avoid the group of putting our hands dirty with the group gamma.
Yeah, so this group is sort of basically consists of something linear plus something compact. So it has so this homomorphism group is rather special. It has a little bit of a Fredholm structure.
Yeah. Yeah, kind of in this lemma too, we have to use, for instance, we have to use the group gamma and some very element to prove that with the linear subspace.
So you don't use this proposition about dimension as a black box, right?
No. I mean, depend what you mean. It's like we use this proposition, we find a linear subspace, and then we know we can play a bit with homeomorphism, and we do
I see.
to push it slightly down because to ensure that we are really below C.
Mhm.
That's a little bit of wiggling there. That we have to really use gamma.
Thank you. Can you maybe define this group with your new understanding of Ekeland-Hofer capacities without kind of specific formulas? So just kind of explain. For me, it was always the most mysterious part, and kind of.
So what I would say, I mean, I hope Helmut doesn't shout at me too much, is to take the group gamma to be really, let me try to write something, to say, let's take gamma to roughly be all elements of the type flow at time t by minus the gradient of AH. You might have to truncate the flow at infinity, but roughly that's what gamma should be.
Yeah, so if of course that looks like a one-dimensional group, so it's actually an infinite-dimensional group,
yeah,
and it has the property that when you study this intersection problem of E minus plus E zero plus with the other, can be you can make a change of variable that the intersection problem is of the form like a fixed point problem, a finite dimensional fixed point problem, like a Lerer-Schauder fixed point problem. So it has the identity plus compact and some finite set of parameters, something like that. So so in some sense, it's built in the definition that the intersection problems you can use Lerer-Schauder degree, which is an infinite dimensional generalization of the Brouwer degree.
Yeah.
So that was the motivation of that group. I mean, and of course it should apply to the flow. So it has, so the homeomorphisms you get from the flow are also in there. But the group is a little bit more generously defined so that you can actually make certain, perhaps computations, yeah, by moving stuff around. And then, of course, we never did the computations, except for ellipsoids.
Yeah. But yeah, in the end, in the proof, the only thing we needed was that it contained the flow of the gradient of the action function. That was the key.
And then I still kind of did not understand your answer to Michael's question. So if I have kind of general Liouville domain, or I mean setting where your capacities with Michael work, right? So how you would define Ekeland-Hofer in this situation? I mean, here you really use decomposition and so
on. My answer was, I don't think I can. It's kind of, I think Hofer and Ekeland-Hofer capacities have been extended to tori.
Yes.
And I kind of, that's the set of examples I know
was. Capacity was extended. I know that Lou and somebody extended, yeah, but not the series.
Yeah, I think there are really technical problems with the H1 half space. So we took the H1 half space because we get a global flow. Yeah, and the flow has nice properties because of the linearity of the ambient symplectic manifold R2N, and that allows to define this group.
So absolutely. So
then And then, of course, if you work in R to n and you have a symmetry, which, for example, you divide R to get T to n, then you can do the same. You do the R to n construction and divide out by the symmetry, and you get another group. Yeah, so that it works. But then maybe for the when Fleur proved the Arnold conjectures for surfaces, so then make finite dimension reduction. So there's a little bit of structure in there. Maybe one could do that in H1/2, but I don't know. I don't know how, and I'm not sure one should do this.
Right. So what I mean, my 2 cents were that maybe Jean, you should sell your result as extension of Ekeland-Hofer's capacities to manifolds, which is kind of probably Michael had in mind the same kind of So it's I think it was known all the way that it's non-obvious task because of fine use of linear structure.
So that you have a more general method. You can do it on manifolds, and in the case of R to n, it just does. It coincides with another construction. That looks to me a reasonable thing to say.
Okay, thanks for the. Let's change the introduction of the paper in that case. Okay, let me maybe get to Zoom.
Okay, so no further questions. Thanks, John, again.